Good day. Today I will be talking about optimization of active and reactive power flow for PV connected to grid system using Newton-Raphson method, reported by Jan-Philippe Ang. In the growing digital age, it is understandable that it comes with a growing power demand, and it is an engineer's responsibility to supply this demand in the most optimal way possible. And given our current circumstances, with our fight against global warming, it is our responsibility to find better ways to fuel our demands through renewable energy. And a great way to do this is by the use of solar cells. This paper takes a look into the optimization of photovoltaic or PV systems by maximizing the voltage output of the inverter, denoted by Vint, and the angle of power, denoted by del, by the use of Newton-Raphson method. So for our materials and methods, you can see in Figure 1 the configuration of our proposed system, where we have our PV array connected to a controller, a sinusoidal pulse width modulation inverter or SPWM inverter, which is also connected to a filter and a transformer, which are all connected to the utility grid and the load. In Table 1, we see the specifications for the solar panel that we will be using, and the radiance value of 1000 watts per square meter and a module temperature of 25 degrees Celsius. So here in Figure 4, in Figure 4a, we see the equivalent circuit, which is our PV array, which is connected in parallel to our SPWM inverter, which is connected in parallel as well to our utility grid with a reactance of XL in between. And in 4b, we can see the phasor diagram, which we will use to find our maximum power, active and reactive power, using the components. So in equation 14, we have a function of MA and del, wherein MA is our modulation index. So we have our VDC over square root of 2 multiplied by A, which is our transformer ratio, multiplied by MA, multiplied by VG, which is the voltage of our grid, divided by XL, which is our reactance. And this is multiplied by sine del minus our Pmax equals 0. And for our second equation, we have VDC over square root of 2 multiplied by A multiplied by MA multiplied by Vg all over XL, which is multiplied by our cos del, subtracted by Vg squared over XL equals 0. And these are the equations that we are going to solve using Newton-Raphson method. And the numerical model can be seen in Figure 7, wherein our Vg was set at a constant 200 volts and our XL, or our reactance, equals 10.0441. So here in Figure 7, this is the modeling that was used in the MATLAB Simulink, and it was used under the following variations. For our first variation, we have a power load less than our output power of the PV system. In the second variation, we used a power load equal to the output power. And I apologize for this typo, but for our third variation, we have a power load greater than our output power. And in this case, it was noted that when the power load is greater, it also draws power from the grid as well as the PV system. So in Figure 9, we see the active and reactive power at the different irradiation levels. And the simulation data tells us that the system was able to reach a peak value of 408 watts of power with the given irradiation values and a peak reactive power of 11.82 var. And the system maintained a steady value of 220 volts at the PCC point, or point of common coupling, which is a point in the network that is electrically nearest to the particular load. So here in Table 3, we can see the different variations and the different irradiation levels. So we have 1000, 600, and 500. And these basically tell us the amount of power being drawn to the solar panel per square meter. And we can see that in our column 4, we see our V at the point of common coupling. It maintains a relatively stable value of 220 volts. And we can see at our PV, we were able to reach a peak of 408. And in figure 10 below, we can see the waveform of the voltage of current and power. And at figure A, we can see it's the utility grid. In figure B, it's the PV system, and C is the load. And as it's worth noting that the current at the load has a smaller amplitude compared to the others. And this makes sense because our current has been deducted or has been reduced by our reactive power, which is XL, and it is strongest at our utility grid. So to conclude this, the simulation of a PV system with optimized values via the use of Newton-Raphson method on the active and reactive power equations was able to stabilize at 220 volts and reach a peak reactive and active power of 11.82 var and 408 watts under an irradiation level of 1000 watts per square meter. And this is an actually relatively successful system because the power factor was at 0.9996. So thank you for listening.